Hi everyone, my name is Huynh. Today I'd like to present our paper, Dynamic Optimal Coding and Scheduling for Distributed Learning over Wireless Edge Networks. My presentation is divided into four parts. First, I will give some background information and the motivation that led us to this research. Then I will discuss about the system model and the proposed solution. Finally, I will highlight some simulation results. As you know, distributed learning have been introduced recently to upload learning data to Edge nodes for processing. By doing this, we can improve the training speed of the system. Also, distributed learning has many advantages and application in practice. It is facing some technical challenges. First, the performance of a distributed system is greatly affected by straggling problem at edge computing devices. A slow edge node may increase the training time of the whole system. Second, the data privacy of the conventional distributed learning is not guaranteed. The reason is that the learning tasks are not encrypted before sending to edge node. Finally, distributed learning over wireless edge networks suffer from wireless link failures. When the wireless links are not stable, the server and edge nodes need to retransmit their data. This will increase the delay of the whole system. To address all the problems, coded computing is introduced as a highly effective solution. The principle of coded computing is to inject and leverage data computation redundancy in order to mitigate the effects of the checkering problem and improve the data privacy. With coded computing, the server now does not need to wait for all edge nodes to send back their computed results. Instead, the server just needs results from a number of fatigued edge nodes to decode the expected result. Moreover, the sub-learning tasks are encoded before sending to the assigned edge nodes, resulting in a high data privacy protection. However, existing works usually ignore the effects of wireless communications. Moreover, the dynamic and uncertainty of checkering problem as edge nodes and wireless links are not considered. In this work, we first propose a highly effective distributed learning framework, leveraging outstanding advantages of coded computing as well as abundant computing resources from multiple edge nodes to securely and effectively execute learning tasks. Then we propose a jointly optimal coding and scheduling framework for distributed learning over wireless networks. Under this framework, one can simultaneously select the optimal code as well as the optimal edge nodes for each learning task, given the uncertainty of the edge nodes and wireless links. Finally, we developed a highly effective deep reinforcement learning algorithm to obtain the optimal policy for the server to minimize the average delay for the whole system. This is our system model. So as you can see in this figure, in our system, we consider a server and several edge nodes for processing learning tasks. And at the server, we have a queue to store learning tasks arriving at the system. And there are many coding techniques. However, maximum distance separable MDS code is the most common technique used in the literature. So in this work, we also deploy the MDS code at the server for processing learning tasks. As you can see in the figure, the MDS code aims to encode K learning tasks into N encoded learning tasks. The encoded tasks are then distributed to N workers to execute. As soon as K workers complete their assigned tasks and send the results to the server can decode them into the expected result. As you can see in this simple example, the server does not need to wait for result from ECNODE 2 and ECNODE N. It can successfully decode the final result by using the result from node 1 and node 3. In this work, we aim to obtain the optimal NDF code as well as the best set of nodes to serve a learning task. To do that, we first formulate the system by using the Markov decision process. In this Markov decision process, we define the state space, the action space, and the immediate reward. The state space includes the queue size, the size of the considered learning task, and the states of all nodes in the system. As we aim to obtain the joint optimal MDS code and the best set of nodes, the action space is the combination of n, k, and a set of nodes. We then define the immediate reward function as minus m, where m is the number of learning tasks waiting in the queue. By maximizing the immediate reward function, we can minimize the number of learning tasks in the queue and thus minimizing the average latency of the whole system. To obtain the joint optimal coding and scheduling policy, the Q-learning algorithm can be used. Here is a diagram to show the operations of the Q-learning algorithm. As you can see, the algorithm can interact with the environment by making action IT and then observe the immediate reward and the next state of the system. The information we will use to update the Q table by using this Bellman equation. The Q-learning algorithm can efficiently obtain the optimal policy when the state space and the action space are small. However, in practice, with complicated system models, these spaces are usually very large. As a result, the Q-learning algorithm may not be able to find the optimal policy. To address this problem, we propose deep Q-learning algorithm to help the server quickly obtain the optimal policy to minimize the average delay for the whole system. The deep Q-learning algorithm implements a deep neural network to estimate the Q-value function instead of Q-table as in Q-learning algorithm. This is the loss function of the deep Q-learning algorithm. By minimizing the loss function, we can update the parameter of the deep neural network, and after a number of training steps, we can obtain the optimal policy for the server. The deep Q-learning algorithm can quickly obtain the optimal policy. However, its performance may not be stable because of the overestimation of the optimizer. To address this problem and further improve the conversion rate, we developed the deep dueling algorithm. In this algorithm, we divide the Q-value function into the value function V and the advantage function Z. This idea is from the fact that in many states, it is unnecessary to estimate the value of corresponding action, as the choice of the action has no impact on what happened to the system. The value function and the advantage function are simultaneously estimated by using this deep dueling neural network. In this neural network, we have two streams of hidden layers. One stream is to estimate the value function, and the other stream is used to estimate the advantage function. These two streams are then combined at the output layer by using this equation. Next, I will highlight some simulation results. To evaluate the proposed solution, we compare its performance with three other schemes: greedy policy, one node, and static optimal code. Under greedy policy, the server selects all available nodes to serve a learning task. The server then needs to wait for all assigned nodes to send back their computed result to be able to decode the final result. And this policy is used to evaluate the impacts of straggling egg nodes and wireless links. Under one-node policy, the server will randomly select one available egg node to serve a learning task. This policy is used to evaluate the typical uncoded and non-distributed learning approach. The static optimal code policy is based on the optimal MDS code proposed in this paper. As you can see, this is the equation to obtain the optimal value of k based on the average straggling parameter and the available egg nodes in the system. And this policy is used to show the performance of a static optimal code that does not consider the dynamic and uncertainty of the system, as well as the effects of wireless links. First, we evaluate the learning process of the Q-learning, deep Q-learning, and deep dueling algorithms. Clearly, as shown in this figure, the conventional Q-learning algorithm converges at a much slower rate than those of the deep Q-learning and the deep dueling algorithm. The reason is that the Q-learning algorithm usually suffer from the slow conversion problem, especially in complex systems like the considered coded computing over wireless network in this paper. Note that our proposed deep dueling algorithm can achieve the fastest conversion rates by using the novel deep dueling neural network architecture. In particular, it can obtain the optimal coding and scheduling policy within 10,000 iterations, while the deep Q-learning algorithm requires more than 15,000 iterations to convert to the optimal policy. Next, we vary the disconnection probability of wireless links in the system. As you can see in this figure, when the wireless links are likely to be unstable, the delay and the number of learning tasks in the queue increase. In all scenarios, our proposed solution can always achieve the best performance compared to those of the greedy and one-node approach. This is stemmed from the fact that our proposed algorithm can learn from the environment to avoid highly straggling wireless links when serving learning tasks. Finally, we vary the straggling parameter lambda and observe the system performance. A lower value of lambda leads to a longer time for processing learning tasks at egg nodes. Consequently, when lambda increases, the system performance obtained by all policy will drop. Again, in all scenarios, our proposed solution achieves the best performance by avoiding egg nodes in which straggling problems are likely to happen. This is the end of my presentation. Thank you for your attention.